Last class, we had discussed about impulse and impulse momentum theorem. Okay, so what was impulse? Impulse was a very large force acting for a very short interval of time. Now here, in the case of collision, what do we have? We have two particles which are moving with some velocities. Let's say u1 and u2. Okay, such that u1 is greater than u2. Then what happens? They'll collide. Okay, so once they collide, they their velocities changes, and this process is known as collision. Okay, so we are going to understand the process of collision by this model of one block having a spring with it, okay, and another block m2 in front of it. So it's given that initial velocities v1 is greater than v2. So then what will happen here? Once m1 and m2 will come in contact via the spring, and then the spring will begin to get compressed. As the spring begins to get compressed, the velocity of the first block decreases and the velocity of the second block increases. Okay, so there comes a moment when the spring is compressed the maximum. Now imagine this situation from the frame of reference of the first block. Okay, if you're sitting on the first block, imagine this. So what would you see? You would see that if you're sitting on the first block, you would see that first block is far away from you initially. The M2 block is far away from you initially. Then as the spring gets compressed, this block appears to move towards you. And at the time of maximum compression, this block is closest to you. And then what happens? This block begins to move away from you. So exactly at the time of maximum compression, what velocity you would observe? You would observe a velocity 0. That means what? At the time of maximum compression, the relative velocity is 0. Okay, that means both of them will have a common velocity. Both of them will have a common velocity. Okay, then finally what will happen? Still the spring is compressed only, so it keeps on applying a force towards left on the block on the left, and it keeps on applying a force on the right on the block on the right. So they continue to lose and gain velocities. So finally this attains some v2 final velocity and this attains some v1 final velocity, and the spring attains the natural length. Then they again part ways. Okay, then they again continue to move with these final velocities. Now how is this related to collision? It is almost exactly similar in collision. What happens? We have, I'll just do that all over again. So we have, suppose, two particles. I'm considering two spherical balls. So first one has mass m1 and second one has, suppose, mass m2. Okay, this one is moving with a velocity u1, and this one is moving with a velocity u2, such that u1 is greater than u2. Then what will happen? At the time of collision, the balls will deform a little bit. Okay, the balls will deform, u1 will decrease, u2 will increase up to the time u1 will keep on decreasing and u2 will keep on increasing, and there will come a time when they attain a common velocity. Okay, such that m1 and m2 both have the same velocity v. This is the situation of maximum deformation of the balls, similar to maximum compression of the spring there. Okay, then what happens? The force on m1 continues to act towards left, the force on m2 continues to act towards right, and then m1 finally has some velocity v1 and m2 finally has some velocity v2. Okay, and from here till here, there is deformation happening. Okay, and from here till here there is reformation. Okay, or we also call it restitution. Restitution is happening. So if you want to find, you can find the common velocity. Why? Because throughout this process the momentum is conserved, because throughout this process whatever is the force acting on m1, equal and opposite force will act on m2. They're applying force on each other. So by third law of Newton, the what will happen, the equal and opposite force acts, so their momentum will be conserved. So since their momentum is conserved, it's not just that the final and initial momentum is same, the momentum is conserved throughout this process. So what will happen, if you want to find v, you can find it this way: m1 u1 plus m2 u2. This is the initial momentum. This will be equal to m1 plus m2 into v. Then similarly here, m1 v1 plus m2 v2 will also be equal to m1 plus m2 into v. Okay, and these two will also be equal, the initial and final momentums. So one equation we have, that m1 u1 plus m2 u2 will be equal to m1 v1 plus m2 v2. Okay, now we have to understand a term known as the impulse of deformation and impulse of reformation. So what is impulse of deformation? You see, when a particular particle, this left ball, is deforming, so it's experiencing a force in this direction. Okay, so from here till here deformation is happening. So whatever is the impulse acting on it in the process of coming from u1 to the common velocity v, that impulse is known as impulse of deformation. If you see the impulse on the system as a whole, it is zero, but on both the particles separately it is non-zero. So how much will be the value of impulse of deformation? You see the left particle, it will be how much? Initially the particle on the left had a momentum of m1 u1, and at the instant of maximum deformation it has a momentum of m1v. So that's why the impulse of deformation, if I just want to write the magnitude, since for the left particle what has happened, the velocity has decreased. So if I want to write the magnitude, I will have to write m1 u1 minus m1. Okay, so this is the impulse of deformation. And similarly the impulse of reformation for this particle only will be how much? It will be m1 v minus m1 v1. Again I'm just writing the magnitude, that's why I have to write this way, since v will be greater than v1 and u1 will be greater than v. If you calculate this impulse of deformation on the other particle, that is m2, then you will have to write m2 v minus u2, because here for the second particle v will be larger because its velocity during the collision keeps on increasing, no? So v will be larger and u2 will be smaller, so it will be m2 v minus u2, and impulse of reformation for it will be m2 v2 will be larger, so m2 v2 minus v. If you v, if you put the values here, you will see that for both the particles it is same. Whatever is id here is id here also, whatever is ir here is ir here also. It has to be same, no? Because same forces are acting. Okay, now there is a term known as coefficient of restitution, which is represented by E. Now, you might recall, or you might just understand from the term also, that coefficient of restitution should mean to what degree does an object deform itself. Okay, so it will be what? Coefficient of restitution will be the impulse of restitution upon the impulse of deformation. Okay, so it will be how much? It will be m1 v minus v1 by m1 u1 minus v. Okay, so now you can substitute the values. So in the numerator you should substitute the value in terms of v1 and v2, and in denominator substitute the values in terms of u1 and u2. So you can see from the previous equations that we have written, yeah, this one, we can use this to get the value of v in terms of v1 and v2, and we can use this to get the value of v in terms of u1 and u2. So just write that here. If you write that here, you'll get so then evaluating it, m1 v1 m1 v1 will get cancelled. So in the numerator you would have v2 minus v1, and the denominator you would have u1 minus u2. So this is the coefficient of restitution. Now what is this thing, v2 minus v1? You see, the after the collision the particle is running away, this second particle is running away with a speed v2, and this one is following it with a speed v1. So v2 minus v1 is nothing but the velocity of separation. And initially this particle was going towards the second one with a speed u1, and this was running away with a speed u2. So u1 minus u2 is nothing but the velocity of approach. So that is why coefficient of restitution is equal to velocity of separation by velocity of approach. Okay, so in general, for any question on collision, there will be coefficient of restitution given. So in a question in general, we'll have E given, okay, and U1 and U2, M1, M2 given. So then the unknowns will be V1 and V2. So we would need two equations to get the unknown. So one equation we would get by the momentum conservation. So which would give us this equation, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Okay, and another equation we would get from coefficient of restitution. So E is equal to what? So E we can write as velocity of separation v2 minus v1 by velocity of approach u1 minus u2, and that in general will be the way to solve the questions. Okay, now there are special cases here. Okay, so special cases, number one, when E is equal to 1. When E is equal to 1, then what will happen? The entire kinetic energy at the instant before the collision is same as the kinetic energy at the instant after the collision. So there is no energy stored in the form of deformation energy. Okay, in the case of spring block system, you can imagine this as there is finally the spring again gets to the natural length, so there is no energy stored in the spring. Okay, so in this case what will happen? In this case, since E is equal to 1, the equations will be m1, first equation will be m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Then second equation 1 is equal to v2 minus v1 by u1 minus u2. Okay, so applying these two, you can get the value in general for the velocities just after the collision. Okay, so in general the value will be v1 equal to, so for e, if you solve e equal to this much, then you would get v1 equal to m1 u1 plus m2 u2 minus m2 e u1 minus u2 by m1 plus m2. So this is in general. For e equal to 1, this would become v1 equal to m1 u1 plus m2 u2 minus m2 into u1 minus u2 u1 minus u2 by m1 plus m2. So what would you get? You would get m1 minus m2 into u1. So you don't have to memorize this. You have to just keep this. I mean, just the equations you should be able to write. Once you're able to write the equations, then you'll be able to get this general value also. Okay, although it is a little bit lengthy, but what's more important is the special case. So you'll be getting m1 minus m2 u1 plus twice m2 u2 by m1 plus m2. Okay, one equation will be this, then v2 will be equal to m1. So you just replace that 1 subscripts by 2 and you would get v2. So you would get v2 as m1 u1 plus m2 u2 plus m1 into e u1 minus u2 by m1 plus m2. So again in this case e is equal to 1, so you would get twice m1 u1 plus m2 minus m1 minus m1 into u2. You see the equations are exactly symmetrical. Just replace 1 with 2, okay, and you would get the second equation. Okay, now here special of special case. So e is already equal to 1, so it is an elastic collision. And very important tip here is that whenever you are given an elastic collision, then don't try to conserve kinetic energy. Okay, unless and until like kinetic energy, I mean the question itself is involving kinetic energy or something. So don't try to conserve kinetic energy. That's not the definition actually of elastic collision. The definition of elastic collision is E equal to 1. Okay, that is the definition. So don't try to conserve kinetic energy, although in the head-on collision it will be conserved. But instead of that, just write E equal to 1, because writing conserving kinetic energy, you'll have second degree equation, quadratic equation, half mv square, so that v will be squared. But when you write E equal to 1, no, it will be a linear equation. Okay, now here what happens? If E is equal to 1 and case A, m1 is equal to m2, then what happens? Initially, if this particle is having velocity v1 and this one is having velocity v2, so m1 m2 both are m, then what will happen? Upon collision, so let's call it u1 and u2 initial velocity. So finally what will happen? Upon collision, this will have a velocity u2 and this will have velocity u1. So the velocities get exchanged. If the masses are same and there is elastic collision, then the velocity gets exchanged. Now second case can occur that m1 is very large as compared to m2. So suppose there is a train, okay, a train going with some velocity v1, and there is a ball here, okay, u1, let's call it initial velocity, let's call it u1. A train going with some velocity u1, and a ball here is having some velocity u2. Okay, so u1 is greater than u2. So here what will happen? Upon collision with the train, you can understand that the velocity of the train will not change. So final velocity of the train will be same as the initial velocity of train. But for the ball, what will happen? The velocity of separation has to be equal to velocity of approach. Now you can see here the velocity of approach is how much? It is u1 minus u2. u1 is greater than u2. Okay, so velocity of separation also has to be same. So that means this is going in this direction with u1. This has to go with a velocity u1 minus u2 greater than that. So it will have a velocity of 2u1 minus u2. Okay, in this direction. Now let's take a numerical example. For example, train is going in this direction with a speed of 10 meter per second, and a ball is coming towards it with a speed of 5 meter per second. So the velocity of approach is 15 meter per second.